Okay, crossing over to inequalities, and here we have a polynomial inequality which states in problem 10 that x squared plus 3x minus 4 is greater than or equal to 0. And in looking for the zeros of this particular polynomial function, we have setting x squared plus 3x minus 4 equal to 0, the factored form, whereupon we have x plus 4 quantity times the quantity of x minus 1 is equal to 0, and setting each of those factors to 0, we have negative 4 and 1. And looking at partitioning separately, while we have utilizing the zeros into subinterval sections. Now we have around the smaller of the zeros, okay, we have with respect to negative 4, our first interval, it will have to be the set of values x less than negative 4. And then bypassing negative 4, we have those values of x less than negative 4 and approaching but not including 1. And with 1 as the second and the last of the zeros, we had the last interval section to be in reference to those values of x greater than 1. And if we take what we have for test inputs, so to test out the first interval, kind of using as a probe, okay, we can select any value x less than negative 4. So negative 5 would fit the bill. Anything between negative 4 and 1, okay, now 0 would be such a value, and anything greater than 1, you could choose, like, let's say the number 2. And applying to what we have for these inputs in x, if I determine, okay, what the y values will be. So if I plug in negative 5 for x, we have like negative 5 squared will be positive 25. 3 times negative 5 is going to be negative 15. 25 minus 15 is going to be 10. 10 minus 4. Okay, that's going to be a positive 6. Now, if I test out the middle interval through using 0 as the input, now we've got 0 from 0 squared, another 0 with 3 times 0, and then we have minus 4. So if I plug in 0 for x, well, we would have f of 0 will be equal to negative 4. And as for what we have with the last of the subintervals, if I plug in the input value 2, so we have 2 squared is going to be 4, and we have 3 times 2 is 6, and we have 4 plus 6 is 10, and we have minus 4, so we have going back to what was 3 times 2, so f of 2 is equal to positive 6. So we have with the sign values, anything we plug in less than negative 4 for x, the result is going to be positive, whereupon we have f of x is greater than 0. Anything higher than negative 4 and less than 1 for the input results as a negative output. So we have f of x is less than 0, and anything we plug in greater than 1 for x, the result in y, or f of x, is going to be positive. So we have f of x is greater than 0. And going back to our inequality, whereupon we have x squared plus 3x minus 4 is greater than or equal to 0, we're looking for those values of x that will make this polynomial function positive as well as equal to 0. So with the equal sign, we had the potential of brackets included along with the parentheses. So for what we have on the side of where we have the polynomial to be greater than 0, we have around the limits where we have going from negative infinity, approaching negative 4, and also we have greater than 0, so we have values between 1 and infinity. And in terms of closing out, now infinities are boundless, so those values remain in parentheses. And since we have at negative 4 and 1, those to be those values that will set this polynomial function equal to 0. Now negative 4 and 1 will be included as solutions in this inequality. So negative 4 will be in the bracket, 1 will also be in the bracket. And so we have for the solution, we will have the union of subintervals, where we will have those values of x less than or equal to negative 4, as well as those values that will be greater than or equal to 1. Okay, for what we have in problems 11 and 12, we're working with a rational function x squared minus 1 all over x squared plus 3x minus 4. And if I take what I have and determine the zeros upon setting the expression in factored form, we have in the numerator a difference of squares, and we have in factoring, I have the quantity of x plus 1 times that of x minus 1. And upon factoring the denominator, I come out to the quantity of x minus 1 times the quantity of x plus 4. And we have with the zeros, okay, from x plus 1, if I set this equal to 0, I have x is equal to negative 1. And x minus 1, this appears twice, once in the numerator and also appearing in the denominator. And if I set this factor to 0, I have x is equal to 1. And for what I have with the remaining factor, I have x plus 4. And the 0 from this is going to be at negative 4. And now, negative 1, this stems from x plus 1, which is exclusively in the numerator. And you can have a zero-valued numerator as long as you do not have a zero-valued denominator. And negative 1 is such a value that works, and thus negative 1 is in the domain of r of x. Now for the value 1, this stems from x minus 1, which appears in both the numerator and denominator. And one might be tempted to say that 1 is going to be in the domain since we have x minus 1 in the numerator. And it would be in the domain if we did not also end up with the 0 denominator. And because x minus 1 is present in the denominator, again, you can have a 0 numerator as long as you do not have a 0 denominator. And since 1 creates that kind of complication, 1 is not in the domain of r of x. And for x plus 4, for which we have negative 4 as a 0, x plus 4 is in the denominator. So we have that negative 4 is not in the domain. Now, working around the zeros and finding out the solution set for what we have in items 11 and 12, I'm going to set up a table of intervals, okay, and rank ordering from the smallest to the largest of the zeros. Okay, so you have going from negative infinity, approaching and not including negative 4. And then we have bypassing negative 4, approaching but not including negative 1. And we have upon bypassing negative 1, we have going past negative 1, approaching but not including 1. And with 1 as the highest of the zeros, we have for the last interval to test out, we have the values of x greater than 1. And to test out the rational functions, okay, in accordance with each interval, again, I'm going to apply input values, each of which will be in the respective intervals. Like I chose negative 5 since that is a sample that is less than negative 4. And we have a negative 2, that is one of the integers, okay, between negative 4 and negative 1, the other one being only negative 3. And 0 resides as the only integer that falls between negative and positive 1. And we have 2 as a value, okay, that is going to be greater than 1. And testing out each value x and plugging into our rational function. Okay, so if I plug in negative 5 for x, okay, so it turns out that we have what's going to be 24 over 6, which will reduce to positive 4. And for the input negative 2, r of negative 2 becomes negative 1/2. R of 0, you would have like negative 1 over negative 4, which will go to positive 1/4. And r of 2 is equal to positive 1/2. And in terms of the sign value of r of x, anything that I plug in less than negative 4, sign value is positive, whereupon we're going to have that r of x is going to be greater than 0. Anything that I plug that is greater than negative 4 and less than negative 1, output is going to be negative, and this will be whereupon our rational function will be less than 0. And for the last two subinterval sections, okay, we're going to have positive outputs. So we have the r of x is greater than 0. Now, for what I have in the case of number 11, okay, so we're looking at where have x squared minus 1 all over x squared plus 3x minus 4 is greater than or equal to 0. So we're looking at where r of x is greater than or equal to 0. And for what we have for the solution, now we'll have just for the limits. Okay, now we have for the comparison portion of the inequality, we're looking at where we had to be greater than 0. So we are involving the limits from negative infinity to negative 4. Also have r of x is greater than 0 between negative and positive 1. And also it had to be greater than 0 where we have from 1 or past 1 on out to infinity. Now, in terms of the enclosures, now we had the equal sign, which signals that we could possibly have brackets along with parentheses. Now, infinities are boundless, so at least negative and positive infinity will be in parentheses. Now, for the zeros, negative 4, negative 1, and positive 1, brackets can only go around those values that will be in the domain of the rational function. Only negative 1 is in the domain. However, 1 and negative 4 are not in the domain. So we have for the enclosures. Okay, so we have a bracket that's going to go around negative 1, since that is the only 0 that is in the domain. And we have, however, 4 and 1 are not in the domain. So we have, in the case of the solution set, okay, so you have those values of x less than negative 4, and we have those values of x between negative 1, where we have negative 1 included on out to, but not including the value 1, and for the rest of the solution, we have those values of x greater than 1. And then where we have, in the case of number 12, where we have the inequality to be the same rational expression to be less than 0. So we're looking at referencing what we have for r of x is less than 0. And so for what we'll have in the case of the solution, okay, now we do not have the equal sign, so we're going to have only parentheses. So we have where r of x is less than 0. So we have those values of x greater than negative 4 and less than negative 1. And that would be the solution set in this problem.